Hello. So we will start a next section, new section in the quantum mechanics lecture series. And in this section we will see the application of some of the time independent Schrodinger equation. And from that solution, from that analysis, we will come to know, we will understand the importance of boundary conditions, the solution of the time independent Schrodinger equation. And we will come to know also about the two fundamental aspects of wave functions, two important, very important conditions that wave functions need to satisfy to solve problems in quantum mechanics. So let us start our discussion. And one thing, the Telegram channel link and the WhatsApp group link will be provided in the description. So you can click on that link to join the WhatsApp group so that I can share the PDF notes of my lectures. So without wasting time, let us start about the new chapter. The first thing that we need to know, this content, these things are generally not explained in your classes, and in many of the explanations that I have seen, the so-called channels that have huge number of views, huge number of subscribers, it is my habit to go into the details of every topic. That is why I love to discuss these things. They are very interesting things. The wave functions that we have studied till now, they are of two types. One is the converging wave function, another is the diverging wave function. Converging wave functions are the so-called wave functions that are normalizable, that can be normalized, and the non-normalizable wave functions, they are diverging. Diverging means they are diverging, they are spreading out. You cannot apply the normalization condition. So it sounds a bit bizarre, it sounds a bit strange, because in the previous lectures I have told you that the wave function must be normalizable to realize the physical states. And thereafter I discussed the free particle solution, the free particle situation, that is very important from this point of view. So you can ask that if the wave function is not normalizable, it is diverging, how can it be accepted? It has to be accepted. You have accepted it as a solution in the free particle case. You have accepted it as a solution in the free particle case. That too was not normalizable, and we learned that the free particle solution is something which is not physically realized. The particle is moving throughout the x-axis. Seen how the uncertainty principle holds in the last lecture. So basically what I mean to say, it is given here. It will be provided in the PDF note. Normalizable wave functions show or signify those wave functions that are where the particle is confined in a region. So you normalize the wave function, and your normalization condition says that the wave function, that the particle will be found somewhere. Wave function, it vanishes at large distances, x equal to plus minus infinity. It vanishes because the particle is within a region. And this discussion is very important when I am going to discuss the infinite square well potential. So please do not skip the videos. These lectures are important. You don't skip videos that are entertaining, then why you skip videos and do not watch the full lecture of quantum mechanics? If you are a student of physics, sorry. So the wave function converges to a point where the probability of finding the particle is maximum, and it diverges, and it is zero at those points which are far away. There is no possibility of finding the particle. This is converging wave function, the first one, and it is encountered in many situations: infinite square wave, potential step, potential barrier, harmonic potential, harmonic oscillator. The next class that comes in is the diverging case. Here it is written, for the converging case, the situation is such that the particle cannot move out of a boundary, and that boundary is created by the potential. The potential VR from which a force is derived. I have told you in the very beginning, F is equal to minus del V upon del R. This is the force that is derived from the potential. So if there is a sudden change in the potential, there is a force, and that prevents the particle from going outside. Diverging wave function presents that have the particles that have no boundary, the free particle, and they have application. These free particle solutions have application in the scattering theory that is discussed in the quantum mechanical lectures. Quantum mechanical scattering, very interesting thing. We will come to that section later on, but for the time being, let us start our discussion. So these free particle wave functions are useful for scattering theory or quantum mechanical scattering. We will see what is a scattering. Now the next thing that you have studied, that is written in most of the books, that the wave function should be well behaved. Now what are the conditions for well behaved wave functions that I have told in one of my last lectures? It should be square integrable, it should be finite, the space derivatives should be finite, it should be single valued, it should vanish at large distances. Let me write it here for your convenience. Wave function well behaved means wave function must be single valued. Wave function must be single valued. Means it should have a single unique value at a point. Wave function psi x should tend to 0 at x plus minus at x equal to plus minus infinity. D psi by dx should be continuous. And finite. These are the three main conditions for a well-behaved wave function, because it is related to the particle. Now the question arises, why wave function should be well-behaved? This is a topic, this is a question that I know it is not in the syllabus. It is not in the prescribed question format of your university, but this is a very conceptual question. It is asked in many situations, why they should be well behaved. Simple question. Because they are related to the particle. The time independent Schrodinger equation that we are discussing here, this is the form of the time independent Schrodinger equation. This is the ordinary form, this is the operator form. So it is a second order differential equation, and the knowledge of the wave function and its gradient, means slope, it makes possible to integrate the equation to find the wave function at a particular point. And when you find the wave function at a particular point, then you can extract information from the wave function regarding the particle, how the particle is behaving in that region. So physically this is the reason. Don't get confused in the mathematical complexities. Try to understand the physics. So covering these topics, we come to the potential infinite well problem in quantum mechanics in one dimension. So the infinite well means something like this. And this is a direct consequence of the free particle solution. In the free particle, there are similarities and dissimilarities between the free particle. See how the similarities are there and how the dissimilarities are there. So this is 0 to A. I am taking the most simple solution. This is the region of X. Here the potential is 0. So for free particle, you observe that the potential is 0. Free particle, potential was 0. So here also the potential is 0. So this is the similarity. This is the similarity. Whereas the dissimilarity, are these two boundaries. At x equal to 0 and x equal to A, there are boundaries. There are boundaries. That was not present in the free particle solution. The free particle was able to move throughout the x-axis, covering the negative and the positive x-axis throughout. But here, what you see, there are boundaries at x equal to 0 and x equal to A. The particle cannot get out of these two boundaries. So there is no probability of finding the particle beyond at the left of x equal to 0 and at the right of x equal to A. The points x equal to 0 and x equal to A are the boundary conditions or the boundaries that restrict the particle, from getting out of the region 0 to x less than A. The particle cannot get out of this region. The potential is so high in this situation that the particle is not able to get out of this situation. So you can imagine something like this, that it is a box and you have a ball here. The surface of the box, it is frictionless, so you are neglecting any additional external force, and the ball is moving between x equal to 0 and x equal to A. It is just moving to and fro. So I am giving you a clue to realize the situation or to imagine the situation. A ball moving between two walls on a frictionless floor. This is a, you can say, classical situation. So classically what will happen if the floor is frictionless and the ball is moving, there is no friction force, and we assume elastic collisions of the ball with walls. So there is no loss of energy, no change in momentum. So there is no loss of energy, no loss of energy or change in momentum, because force is 0. Change in momentum. So this is the classical situation, and you have studied the classical situation in many textbooks. What we are interested here to find out the quantum mechanical situation. What will happen in the quantum mechanical situation? What does quantum mechanics say, and how its results are different from classical mechanics? So this is a situation like a well, kuwa, that is of infinite depth. There is no chance for escaping that well. So let us see what happens. So what we have here, outside the well, outside the well, psi is 0. Why psi is 0? Because the particle cannot get out of the well, cannot get out of the boundary or the region. So we want to know what will be the solution inside the well. So we want to know what will be the solution inside the well. Outside the potential, outside the particle is not present, so wave function is 0. Now let us see the situation inside the potential well. Here you have a similar thing and try to concentrate on the topic. This is very important. When we are considering inside the well, potential is 0, similar to free particle. Similar to free particle. In the free particle case, we had a similar situation where the potential was 0. So inside the well, we have the same condition, but there are boundaries. So what will be the Schrodinger equation inside the well? Time independent Schrodinger equation inside the well. In any situation, when you have to solve a problem like this, the strategy is to write the solution Schrodinger equation with the proper potential and then find the solution of the Schrodinger equation. That will give you the wave function. So inside the well, the time independent Schrodinger equation, it reads, since potential is 0, it reads minus h bar square by 2m d2 psi, and it is dx square is equal to E psi. The particle has total energy in the kinetic energy form. So you can simplify this situation taking this constant this side. So what you have is d2 psi upon dx square is minus 2m by h bar square E psi. This is not something which is very difficult. It is a simple thing. This is mathematically very simple and physically it is very interesting. So we can further write this equation 2 in a convenient form if we assume this thing as k d2 psi by dx square is k square psi, where k is, sorry, it is minus k square psi, where k is root under 2me by h bar. Now this quantity is of most significance in the analysis. K is, I have told you in the last lectures, but in case you have not seen or you have not understood, this quantity is, sorry, it is h bar. This quantity is k is equal to p by h bar. So it is 1 by lambda. So this quantity is related to wavelength of the particle, and wavelength depends on momentum. So if there is a change in momentum, there will be a change in wavelength. In most of the situations I have seen, people take this thing as a mathematical simplicity and don't understand the physics. Try to understand the physics. Particle that will change when there will be a force, and change in wavelength means change in momentum. So let us move further. So what we have seen here, that the particle is moving, potential is 0 inside so the particle has total energy in the kinetic energy form, so it will be always positive. The particle has total energy as Ke, so we can easily consider that E is always 0. E is always greater than equal to 0. Now what will be the solution of this differential equation? d2 psi upon dx square is minus k square e. The solution will be of a very interesting form, and we have seen this in the case of free particle. There we took the exponential solution. Here we will consider a different solution. Why? Because there is a boundary. Since the particle is in a boundary, that is defined by x equal to 0 and x equal to a, and as I told you the classical example, particle is moving between the walls in a to and fro manner. I am describing this in the most simple way, in the to and fro manner, like an oscillation. So we can take the solutions as in the form of periodic functions a sin kx and b cos kx. This is perhaps equation number 4. This is also the solution if you consider in the mathematical point of view the solution of a differential equation. So this is simply a simple harmonic oscillator in the classical sense. Classically, simple harmonic oscillator, SHO. So what you are getting, wait a bit here, try to understand the physics. So the wave function shows a oscillatory behavior, means the particle, as I told you, it is oscillating between the walls. It is moving to and fro between the walls. And that this solution is consistent with the physical situation. We will see what is the meaning of sine, because it is also the solution from the mathematical point of view. We will try to understand what is the physical case. Now you have psi x, a sin kx, b cos kx. To get the complete information, what we need to know plus b cos kx, we have to find these. Then only we get the complete solution. So to find A and B, we use boundary conditions. Boundary conditions. What are the boundary conditions? Psi is equal to 0 at x equal to 0 and x equal to a, because the particle is moving between x equal to 0 and x equal to a. It is not coming to rest at these points x equal to a and x equal to 0. So the wave function is 0 over there. And if we evaluate this quantity, this is equation number, what is the equation number 4? So psi x, put here x equal to 0 and left hand side is 0, sine 0 0, b cos k 0, 0 cos 0 is 1, so b is equal to 0. So what we see, that the wave function, the solution of the time independent Schrodinger equation has only one periodic quantity, that is a sin kx, b is 0. This is consistent with the boundary conditions. I think this much is clear. So we will apply the other conditions also, the continuity conditions. First let us check this. So psi x is a sin kx. Now what will be psi a sin ka, and we have seen that a sin ka is again equal to 0. This should be equal to 0. Now this equation will be 0 when either a is 0 or sin ka is 0. Now, which one is applicable? Which one is applicable? If A is equal to 0, we again get a non-normalizable solution psi x equal to 0. This means this is a contradiction with the situation. If psi x is equal to 0 inside the region x equal to 0 to A, this means the particle is nowhere there, but we know that the particle is in between x equal to 0. So A cannot be 0, as it means psi x is 0 inside throughout means if this is the region, everywhere psi x is 0, that means the particle is nowhere. Means the particle is nowhere. This is contradictory. This is not acceptable. Is nowhere. So this cannot be the solution. This cannot be acceptable. For sin Ka, A sin Ka to be equal to 0, Ka should be equal to pi. Simple, sin pi is 0 and any integral pi is also 0. There can be negative solutions also, as sin minus theta is minus sin theta. So it can be managed in the quantity A. So what we are left here is Ka is equal to n pi, and K, remember what is K? K is equal to n pi by A. Pi is constant, A is constant. This K varies with n, so we write the subscript n. Subscript n shows that K depends on n. Now what is K? K is root under 2me by h bar, means it is p by h bar, means it is 1 by lambda. Lambda is the wavelength. So at some points the wavelength is 0, at some points the wavelength will not be 0. That depends on n. So what we have, K depends on n means at some points Kn is 0 and at some points it is not 0. It is not 0. Then what does this physically show? This shows something like this. Shows something like this. This is the point 0. This is again 0, again non-zero, negative side, minus solutions, plus solutions, minus 0. So your oscillatory behavior, it is due to the wave which is confirmed by this solution. So we can now write n pi by A. N can be 1, 2, 3 and everything. N cannot be 0. If n is 0, this means K is 0. K 0 means 1 by lambda is equal to 0, means lambda is infinite. That is not acceptable. Why it is not acceptable? Because the particle is confined in a region. K is equal to 0 or 1 by lambda is equal to 0 is not acceptable. Is not acceptable because the particle has boundaries. The particle is in a boundary. Wavelength, this is 0, means lambda is infinite. It means if we have a wave, its crest is here and its trough is somewhere here. Infinite wavelength. The second point is again at infinite distance. This is not possible. You have the particle in a confined in a region. So all the crests and troughs, they have to be present inside this region. whatever crest and trough, it should be here in this region. So we cannot accept the solution that k is 0. I think this explanation is sufficient. Now, the most important thing that we can do, that if kn is equal to n pi by a, how to find E? How to find E? So what we observed, kn square is 2me by h bar square. So a is n square, putting this value of a square into h bar square by 2m. So what you get? N square pi square h bar square by a square 2m. Energy of the particle. Now this energy, it is directly proportional to n square, a number. When a physical quantity is defined by numbers, number means n equal to 1, this is one state, this is varying with n, is defined by numbers or varying with integers. So, or then it is called quantization. Then it is called quantization. This is the principle of quantization. You have studied in charge quantization. Q is equal to NE. So the energy is quantized. Energy is a function of n. N equal to 1, you have E1 is h bar square, then pi square by 2ma square. This is the lowest energy. N equal to 1 means k1 is pi by a. Now we will come to more interesting things in this content. Lowest energy or ground state. Now see, again a very interesting situation is coming here. K1 is pi by a, and what is K? K is 1 by lambda. K was P by H bar, so it is 1 by lambda, related to lambda. So this what does this equation say? This equation is relating or connecting the de Broglie wavelength with the dimension of the box. I am calling it a box, or you can dimension of, you can call it well, of the well or the region. And whenever we have an interaction of wavelength and geometrical properties, size of the object, depth of the region, we are getting results similar to what? Diffraction. So our results will be similar to diffraction. Our results will be similar to diffraction. This is the most significant thing about this infinite square well or particle in a box solution. I will continue with this lecture with the conditions of orthonormality and completeness that are fundamental properties of the time independent Schrodinger equation in infinite well. So please watch the videos, subscribe and like. You will learn a lot of things, I can claim. Thank you.